I'm working in the biostatistics department on prediction modeling, and I'm very happy to present today Diana. And unfortunately, I didn't practice her last name, Shamsutdinova. I should have practiced this, sorry, Diana. Diana is actually a PhD student of me and Angus Roberts, and she does her PhD in predicting diabetes in people with severe mental illnesses. And she became very interested into survival analysis models. And she will present today her work about combining the Cox regression with more modern machine learning methods to boost predictive performance and to preserve interpretability. But before Diana starts, just a brief bio of her. So Diana studied math in Moscow State University, and then she worked for 10 years or more than 10 years in the financial industry, I think in London mainly. And then she started doing a part-time MSc in neuroscience and psychology of mental health here at the IOPPN. So that's this new or relatively new online neuroscience and psychology MSc. And afterwards, she decided to do a PhD in our department about, as I already said, predicting diabetes in people with severe mental illnesses. And she will present today a part of her more methodological work, and hopefully in a few months we can also hear about her more applied methods. But yeah, thank you, Diana, for agreeing to present today, and I will hand over to you. Yes, if anybody has got questions, please put them into the chat. I will collect them, but of course after the presentation you can also ask Diana questions in person. Okay, great.
Thank you very much, Daniel. Thank you. It's a pleasure to see so many of you today, and I want to say thank you for spending your time, for interested in this topic. And I'm gonna start sharing my slides now. So as Daniel already said, I'm a PhD student at Biostatistics and Health Informatics, and today I'd like to present you some of the results of the project that we're working on, the Ensemble methods and survival analysis. So first, I'm going to talk a little bit what survival analysis is and what methods it can employ, the aims of current project, and then methods. I'm going to briefly describe the Cox proportional hazards model and survival trees, and the ensemble methods that we want to test, the combination of these two. And then we are going to see the results and some conclusions. So let's start from survival analysis. This is part of data analysis that deals with time to event. And by that, I mean that, for example, we observe a population and there is a certain phenomenon that's happening in it. And we know we're basically interested in how time of event is distributed in this population, or, for example, what proportion of the population is likely to have an event by a certain time, or what is the speed, or what's the how many of population are likely to have event per unit of time. And mainly, we're interested in how do the risk factors impact time to event. Right? So, for example, I work on predicting diabetes onset among older population or among people with a severe mental illness. And you can ask questions like how different body weight, BMI, affect the chances of having diabetes within a certain time. The methods of survival analysis that are available right now, I would roughly divide into 4 groups. First two are statistical methods, and the second two are algorithmic or machine learning approaches. And it's not all of them, but I think it's a nice representation of what's available. And the parametric models, they assume there is a certain distribution, statistical distribution for the time to event. The semi-parametric methods and the main model, the very famous model, is the Cox proportional hazards model, and it basically assumes that there is some baseline function, survival function for the whole population, and then we shift it for each individual depending on the risk factors, on the individual risk factors. Then there are tree-based algorithmic approaches, so it's survival random forest, survival trees, and there are more complex machine learning algorithms such as gradient descent, gradient boosting, survival support vector machines, neural networks, etc., etc. I think that the machine learning came to survival analysis quite recent, and I think we're still seeing new methods emerging or being adopted for survival analysis. What I like about the methods is, or what I can say is that the flexibility of the models from group 1 to group 4 is increasing. So the relationship that you can capture with these models are more complex, right? But then interpretability is less and less possible. And for example, the machine learning, the neural networks, deep learning algorithms for survival analysis are really hard to interpret, and they're more like black box. So what we are trying to do here in this project is to combine the groups number 2 and number 3, which are probably the more balanced in terms of flexibility and interpretability. And I'm trying to combine both of them such that you can get the best out of each of these approaches, but then try to overcome the disadvantages of these methods. And the Cox proportional hazard models is particularly robust, fast, and it's very easy to interpret. It's pretty much like linear regression, right? In the classical analysis for survival analysis, this is Cox proportional hazard model. And the problem is that it's by default, it does not capture interaction between the risk factors, and it doesn't capture nonlinear terms unless you explicitly edit it to the linear regression, right, that you run. And the tree-based approaches are exactly what can overcome this disadvantage. They basically can account for nonlinear and cross-term effects, but they're more difficult to interpret, and they have a higher number of model parameters that you have to tune, right, and it can overfit. So let's see if we can combine the two to boost the overall performance. So that brings me to this slide, which is the aims of the present work. And here I'm trying to combine the Cox proportional hazard model and the tree-based survival models to predict probability, specifically to predict probability of an event by a certain time, in a way that first it boosts predictive performance. So we want ensemble method to be better than any of the underlying methods, right? Secondly, we want to capture both linear and nonlinear relationships. Thirdly, we want to quantify the contribution of nonlinear terms, right, added to the linear terms. And then we want to have some insight into nonlinear terms in the data. We want to see where they are. And we want to use tree-based machine learning algorithm, but still to preserve interpretability. So there are similar ideas in previous research, and you can browse this if you want this presentation, I can send it to you. But basically, the main advantage or the feature of our project is that we focus on interpretability and on quantification of linear and nonlinear effects. So now I'm going to briefly overview the Cox model and the tree-based survival model, so we know what we're combining here. So the Cox model is, look, first of all, we can always have the survival function, the hazard function in survival analysis, and survival function is just the probability to survive past certain time, and the hazard function is instantaneous probability of event for everybody who is event-free by time t. I could write the formula how the hazard depends on survival, but I guess the description is more important, and that's what for example, the hazard function of 0.1 means that it's 10% of population is likely to have an event at that particular time out of everybody who are still alive or who are still event-free by that time t, right? So the Cox model specifically assumes that there is a single baseline hazard function for everybody, and that individual hazard is just the multiple of that baseline hazard function, right? So the hazard function actually depends on the time. So it could be that, for example, after the surgery, there is high chances to, well, to die right after the operation, but like less so if you already survive certain time. So your hazard function will be higher right after surgery, but lower after that. So it can be time dependent. But then for each particular person, you multiply this time dependent hazard function up and down. And Cox model assumes that this multiplicator is constant in time and that it depends linear on the risk factors. And it basically means that every two observations have proportional hazards. And this is why it's called Cox PH, Cox proportional hazard model. This is a small illustration. So for example, if you have a constant hazard function, it corresponds to exponentially distributed time. But the point is that if you move the hazard, for example, from 0.10 to 0.2, the survival function, which starts at 100%, everybody's alive, right? It's at time 0, and then it falls down. So this is how the shape, right, changes for the multiplicative change in this hazard function. Now let's look at survival trees and survival random forest. So the survival tree works that you have the whole population at start, and then you look for specific division in the form of some parameter, age or BMI or anything else, right? Below a certain threshold. So you look for which parameter in which threshold to choose such that the two separated populations are mostly kind of are less like each other. So you kind of want to separate the population into two less heterogeneous, or inside them to be more homogeneous, right, populations. And then you divide, and then by the end you have certain number of leaves. And in each leaf, you assume that population is more or less homogeneous in some way. And then you can use just single survival function for each of them. And normally you just do some simple approximation using non-parametric survival curve. The survival random forest works like by training many trees, survival trees, like 500 or 1000. Basically, this is the model parameter. And then you average for each particular individual, you drop and you see which leaf it falls into, and then you average the prediction from each tree for the individual. Okay. And now that brings me finally, so we reviewed what the Cox model is, what the survival tree is, so now how do we combine them? So the first idea is to first go and do everything linear that you can. So we fit Cox proportional hazard model, and then we find from out of it, we take the resulting survival probabilities, and then put these resulting probabilities as a new risk factor, right? So we already had age, BMI, and everything else, gender, etc., and then we also have survival probabilities backed from, or event probability from, the Cox model. And then we fit survival random forest on everything, including this new risk factor. And then we cross-validate the whole model, right? We basically evaluate the model. So the rationale here is to split linear and non-linear steps, because our random forest already knows the answer from the linear model. So we see basically by looking at the difference in predictive performance of the first step and second step, we could see what's the marginal contribution of the non-linear terms. And also the interpretability is pretty much as follows. So we have the regression coefficients from the Cox model, which represent the linear terms. So we know exactly the coefficients, right? We know how much, what is the hazard ratio brought by each risk factor. And then we know the difference in performance, which quantifies the predictive value of the nonlinear effects. So this is the pictogram here. So Cox, then we take the predictors from or probabilities from the Cox model as risk factor, and then we do the survival random forest. The second method goes in the opposite way. So first we do the nonlinear tree-based algorithm, and then on top we do the linear. So the exact way is we find out what are the main risk factors, what are the main predictors which work the best in the tree algorithm. So we use a special function, variable importance function from survival random forest. And that gives me the list of the most important risk factors. And then we only use these risk factors and grow just one single shallow tree with these predictors. And we treat the final node. So we build this tree where the number of clusters not more than 10. Or you can kind of regulate this, but not more than 10 in my case. And the tree clusters our populations, right, in few subpopulations. And then we built a separate Cox model for each of the clusters. The rationale for that is that Cox model assumes that there is a single baseline survival function or hazard function, right? And then we shift it up and down. But what if we can first divide the population into few subpopulations which are more similar to each other, right? And then we use Cox model. So then we have separate baseline regression, baseline hazard function for each of the clusters. The potential issue here is the stability of the model, because we just grow one single tree, and the trees are basically, it's known that if you change your data a little bit, it could be that the tree that you build will look different, quite different. So that's a potential issue. And for that, exactly for that reason, I did this first step where I make sure that I know what are the most important factors to build the tree, and I just use them to build my shallow single tree. So ensemble number 3 is kind of similar to ensemble number 2, but probably simpler. So the first 2 steps are the same. So we find the most important factors and we grow a shallow single tree, but then we build just one Cox model. So as if just a usual, very simple Cox model, but we also add a new categorical variable for each observation, which indicates into which cluster on this tree it belongs to. And this is actually a very interesting idea, because in this way, you automatically find nonlinear predictors. Because if you remember, the tree builds it subpopulations by saying if age is above that threshold, you go right or left, right? And then the next time it says if your BMI is above or less the threshold, you go left or right. So it means that to belong to a certain cluster means that your age is, for example, above X and BMI below Y. So that represents both nonlinear and cross-term effects, right? Where age times BMI shift the way they work in the model. I guess the rationale is exactly that. So we use tree to automatically identify nonlinear predictors. And the interpretability is also very easy, because actually it's even easier out of the 3, because you just have single Cox model at the end, and you know exactly, and you can display the tree to see what are these clusters, what do they represent. And I'm going to show you on the examples, right, very soon. And also to mention, so I used different. So the way you build the tree can be different. And I used two different algorithms, one from survival in the forest and the other one from R-part, from different package. And so basically the ensemble 2A and 2B, they differ in the way I build the tree. So how do I assess what is best, what's not? I assess it in three qualities: discrimination, calibration, and interpretability. So discrimination is the ability to identify high-risk individuals. So high risk, who is high risk, who is low risk. So this is discrimination. And as usual, I'm going to use area under the curve, which is for binary effects is kind of similar to the C statistics or concordance index. And that represents the probability that observations with positive and negative outcome will have probabilities in the same order, that probability is higher for those who have an event than for those who don't experience the event by a certain time. Calibration is something that is not always looked at, but I think it's very, very important for health research. And that's basically how estimated probability corresponds to observed share of individuals with the same risk factors. So for example, I say my prediction is 0.2. And that means that there is 20% probability that a person experience, for example, has is going to have diabetes in the next 10 years. So I want that this 20% to correspond to the fact that in the data, if I take all people with similar characteristics, out of them 20% of people will experience the event, right, over 10 years time. And I want this for each, for like across all the probabilities. So this is the calibration. And it's assessed with the calibration slope and intercept, and slope is exactly, so if the slope is 1, it means that there is good correspondence, right, of what you predicted and what you observed, the prevalence. Intercept is the calibration and the large. It kind of overall shows how systemically, if you underestimate or overestimate the risk of people with your prediction. And finally, the interpretability, that's one of the aims of our project, but there's no measures. So I think I came up with the two questions that I want to ask, which is, does it give an insight into the nature of nonlinearity, this ensemble method, and is each prediction easy to explain? So let's now, and then methodologically, we also use cross-validation or nested cross-validation. That means that I take all the data, and then we took 80% of the data to train the models, and then we tested the models. We compared how the predicted with the observed results on the rest 20%. And then we did it 5 times using different test set, right? And then we averaged. So the resulting, the numbers that I'm going to show you on the next slide are the average across these 5 iterations. There's also another layer. So this is what's called nested cross-validation. That's on the train set, you kind of do another loop of cross-validation to calibrate the model parameters like tree depths, number of trees for random forest. And then once you found that, you retrain it on the whole train set, and then you check the model on the test set. So that's pretty standard. I know, I probably think you know it already, but that's just to make sure I said this. And there are 5 data sets to test the methods. So 3 of them are simulated data, and 2 are the real data. The simulated data, number 1 only has linear relationships, number 2 has strong nonlinear relationships, number 3 has cross terms, then there is number 4, which is English longitudinal study of aging data, and for the outcome of diabetes onset, which has around 6,000 people there, and I use 12 predictors here. And there's another data set from survival package, which has real life data of German breast cancer study group of around 700 people. And the outcome there is death or relapse of breast cancer. So that's the data number 1. And basically, it's hypothetical, it's heart failure. I use BMI, hypertension, gender, and age for predictors. And basically BMI, higher BMI, older age, and present hypertension increase chances of the event, and gender is essentially a noise factor. It does not affect the chances of event happening. So this is the results. So what I did is I took just the Cox model, nothing else, just the survival random forest as baseline method number 2. Then there is ensemble method number 1, where we first do Cox and then use the survival probability to train random forest. Then ensemble 2A, where we build single tree and then we use Cox model for each leaf of the tree, right, with different tree algorithms to A and to B, and ensemble 3, where it's a tree model, and then you put the clusters and indicators as a new risk factors for the Cox to single Cox model. So here I'm not going to stay on the slide for longer. So this is a linear relationship, and you see everything performed well. Nothing performed much better than others. And you can see that looking at the slope and intercept, so we want intercept to be 0, so we don't overestimate or underestimate, and we want correspondence, so slope 1. So 2B is not so good, everything else is good. And also you can see that the Cox regression coefficients guessed it right. So my simulated age coefficient was 0.4, BMI was 1, hypertension 0.7, and gender was 0. So it all works as expected. So more interesting results are for the nonlinear dependencies. So in this data, it's the same as in data number 1, but I use the step function for BMI, assuming that if BMI is normal within 1 standard deviation from the population mean, it does not affect heart failure symptoms. If it's very high, it does increase, right, the chances of heart failure. So this is something that shouldn't be captured by the Cox model, but something that I think could happen in reality, where if a person is very has a low body weight or very high body weight, that could put pressure on cardiovascular system, right, and lead to heart failure. But within the normal range, it doesn't. And the other thing is the impact of age. I added the step function here, that after the age of 55, which corresponds to 0.33 in standardized terms, because my population has mean of 50 years, also 0.33 is 55. So there is the step function here. So let's see the results. And here, to our satisfaction, you can see that all the tree-based models, they brought 4 to 5 points to the AUC statistics. You can also see that the calibration is better, right? And also you can see that like the 2B again didn't work very well, and the 2A was better. Now, let's say I didn't know that there was some nonlinear terms, and I didn't know what they are. Let's say I wasn't the one who simulated the data. So how do I use these ensemble methods to get insight into where this nonlinearity is? So first of all, I look at the results of the Cox model, and I'll see that age has a very high, so it's all standardized, right? So age is for 1 standard deviation, BMI for 1 standard deviation, hypertension for having it or not having it. So you see that age has a very strong impact in linear terms, and hypertension as well, but BMI has 0 and gender 0, right? Okay, so now let's look at the next slide, and this is the this single tree that I trained, right, for ensemble method 2A and 2B. So they both, these methods, they have the same first two steps where we find what are the main risk factors, most important, and then we build this shallow tree to cluster. So the clusters are like that. So don't worry that it's 4, 5, 6, 8, and 9. That's how it names it, because 1 is here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So, but the leaves are basically 1, 2, 3. So we have 5 final leaves. And this is like magic, right? So basically this tree guessed exactly right that there is something going on at age around 0.32, right? And BMI at around +1 and -1. And same for the other 2B, right? The other algorithm for tree. It also has the age division at 0.39 and BMI at around -1 and +1, and then it even corrects to 0.31, right? So this is pretty cool, because by looking at the trees, you can see where the potential switches in the regimes are. But at the same time, you know, if everything were linear, it would still build some kind of tree. So you're not sure if this tree is actually the represent the nonlinear or linear kind of subdivision in the how survival works in this population. But combining this picture where BMI has zero impact according to the Cox model, but here BMI is very important. You see, it's like the second step. It all uses BMI to separate. From here, I would say, oh, okay, there's something going on that BMI on average works as 0 in the population, but actually it works very differently in different clusters. And then again, can we get more insight into the data, right? I could say that ensemble number 2 is less informative than ensemble number 3, because but let's go in the order. So first we look at the ensemble number 2, and what I did here, I found the most important factors. I built a shallow tree, as we saw before, right? And then for each cluster, we built separate Cox model. We can actually display what are the parameters in each of the subpopulation that it built. The problem is it's still not going to show us that the BMI impact is like that. Why? Because it basically clustered everybody here into one cluster, everybody here into another cluster, everybody here into another cluster. But in each of the clusters, right, the BMI is, the impact of BMI is exactly the same. So it will all go into the impact of BMI here, will go into the baseline hazard, but not into the impact of BMI itself, right? Because everybody are the same in this cluster. So here you would still expect to see like around 0, right, for everybody. Or maybe because here there is like another step function, that's why you have this -0.35 and +22, because there is some separation. But in the middle, it's still around 0. So this ensemble method, although it kind of, it's logical, right, that in each of the clusters, resulting clusters, you will see BMI still impact of around 0, but it doesn't give you much insight into how the step function looks like. So for that, I will go into ensemble number 3, which is which just use these clusters as a new risk factors for the single Cox model. And interestingly, all the clusters are have very high significance here, and that means that you guessed it right. So the tree guessed it right, and then by looking at the tree, we can see what they are. So cluster number 4 is age below 0.33, BMI between -1 and +1. So this is our baseline, and that's what we know is basically if for younger people with BMI between -1 and +1, that's pretty much the lowest risk possible, right? And this is the baseline which the model chose. Then cluster number 5 is for higher BMI, and cluster number 6 for low BMI. And being there, makes 3 times or 2.5 times risk, the hazard ratio, right? 3 times likely to have diabetes. And this is on top of some linear impact of age, right, already, which it's, again, it calculated in the right way, 0.33, right? So the slope that I model was 0.4, so that's pretty close. And then we also know that for very, did I do it right? Cluster number 8 and number 9, I think, yes, so sorry, that's not right. So here the age is above 55 for both of them, cluster 8 and 9. And it just the BMI is different, but you see that it gives you 6.5 or 8.3 times higher the risk. And that's because there is a step function for age above 0.33, right? So this is where you can get exactly the insight what's going on. You see that BMI between between -1 and 1 is the lowest risk, and then for anything very high, very low, that makes the risk 3 or 2.5 times higher. And for older age, it makes it 6.5 or 8.3 times higher. So very easy to interpret. And actually, so if you didn't know what the data is, it's kind of easy to guess what it is, right? What this non-linearity are, what they are exactly. So we tick kind of all the boxes. We have the linear age component here. We have the nil BMI for the baseline cluster 4. Then we have the same hypertension impact for all clusters. And then we have the BMI switch at -1 and +1. So ensemble number 3 can be used to identify nonlinear cross dependencies in this case. Now, even more interesting data with interaction terms. That here I use the interaction between hypertension and age. That so I assume that hypertension has more impact on heart failure for older people than it is for younger people, right? So sorry. So for example, here this is the illustration. This is the survival curve, and between the black and gray lines, this is the younger population with hypertension or without hypertension. You see there is not much of a difference here. There is some, right, but not much. But for the older population, the difference between the two survivals are quite higher. So it means that the hypertension does have more high impact for in older age than it does in younger age. And again, here we see that all the tree-based models perform much better than the baseline Cox model. So 10 points right on top. And the calibration also is quite good. Actually, for the just random forest calibration is so, right? But the ones that combine linear, nonlinear, it's much better. And again, 2B is not so good, but like 1, 2A, and 3, they're okay. And similar logic, right? How do I look into the data? How do I find where these non-linearities are? I would go here. I would first look at the baseline Cox regression coefficients. Again, I see BMI has 0, hypertension has a lot, age not so much, gender 0. And I look at the trees, and in the trees, it's all about hypertension and then BMI. So I would say, okay, there's something going on with BMI again. However, so look here, although the performance is very good, none of the trees guessed the hypertension times age interaction term. And I think that's because I underdid the, I didn't do enough, I didn't allow enough depth for the tree to capture it, because I played around. If I increase the number of like the depth of the tree, how many times I can separate, right, the population, then the next time will be separation by age. But I limited the tree depths. And funny enough, this actually maybe that's not right. Maybe I didn't nested cross validation and it chose the 3, but sometimes to get a better insight in the data, maybe you should allow a higher number of clusters and more depth into the tree. And here you can see, again, we look at ensemble number 2 results where we have Cox model for each. So we trained this model, right? We trained the tree, and then for each cluster, we built its own Cox model. And this is the coefficients for the Cox model in each of the cluster. Well, the hypertension is NAY because hypertension is either everybody has 0 or everybody has 1, right? So the population does not differ in hypertension in none of the clusters. So that's why there's no estimate of this parameter here, which is expected. But then the higher chances for heart failure for hypertension equal 1 will be presented in the baseline, the higher baseline hazard rate, right? Again, the BMI is always 0, so we have the same effect as before, so we can't really guess from here. So we go to ensemble number 3, and we go into the cluster 5, 6, 7, and we see that the clusters are actually very significant. Funny enough, the cluster number 7 didn't calibrate. Probably there were not enough people in that cluster. Maybe I should simulate it with a higher prevalence. But basically, you can see exactly what the clusters are, and like see that what nonlinear effect each of this condition has, right, on the individual predictions. And now, so that's probably the last 5 minutes of my talk. So we have some time for questions. This is the two real studies, the ELSA study. So that we worked with Alessia, who's listened to this presentation, and she's the expert of the ELSA study. But what I did here is I looked at the at few predictors and the onset of diabetes, and you can see how, for example, one of the main parameters, BMI for diabetes incidence, that's how the survival function looks like for them, just to illustrate. And the results are interesting, quite similar to what we saw for the data number 1, meaning that it kind of suggests that there's no strong nonlinearity because none of the ensemble methods worked better, and some actually worked worse, right? So why did they work worse is because they overfit, right? They tend to overfit because on the train set, from the 75 at baseline Cox, it moved to 96 for random forest, so like 82 here, but then on the test set, it dropped down. So these models tend to overfit the data. But the calibration was also different, but not so bad for ensemble methods, I guess at par with the baseline Cox model. I could see, so interestingly, you could see what are the risk factors, what their impact was from the baseline Cox model. And to give some interesting results, we also included the polygenic score for type 2 diabetes. And you can see that having a polygenic, so having genetic predisposition 1 standard deviation higher than on average in the population makes you 1.4 times higher chances to have diabetes, to experience diabetes in life. So it is pretty significant, and like per 1 standard deviation is 1.4. So again, it kind of shows that there is good genetic contribution to diabetes onset. Because we already had the age, gender, BMI, and cardiovascular disease, and hypertension, and exercise, and wealth. We had lots of things, but still we have that genetics does impact, and quite a bit, right? The diabetes onset. But then what I wanted to show you here, that although our results do not infer nonlinearities, we can still guess some, because when I look at the ensemble method number 3, right, and when I look at the clusters, they're all quite significant, and they all have like 2 times 7, 3 times 3, 5 times the baseline risk. So interesting, there could be some switch, like qualitative changes in this cluster in terms of diabetes incidence. So when I look at what the definition of cluster number 4, it shows that if the age is, standardized age of 0.51 is 60 years old. So if a person is above 60 years old, right, but the BMI is lower, but low BMI, then it's 2.7. If a person is basically has higher BMI between 0.3 and 1.4 in standardized terms, this is between 27.5 and 33 BMI, which is like a really, really high BMI, right? Then you have 3.3 times the risk. And for very high BMI, you have 5.5 times the risk. And what it says, basically translating it to words, is for low BMI, older age has a nonlinear added impact on diabetes at around 60 years time of 2.7. And then the high BMI has an added nonlinear impact, which does not depend on age, right? And if it's if it's up to 27.5, if it's above 27.5, it's 3 times the risk, and if it's above 33, it's 5 times the risk. So even though there are no signs of strong nonlinear effects, you could still have some qualitative changes and like step functions using the ensemble method number 3. And finally, the another real data set on the cancer data that actually does show that there is some nonlinearity, because all the tree-based algorithms worked quite much better than the original Cox model, and they also had better calibration. You see, so here the intercept is 0.5, which is quite bad, but like random forest is around 0 and 1, and I think the rest are not so good though. I'd say that looking at these results, it kind of suggests there is no linearity, but it also suggests that there is low stability. And maybe it also just shows that there's not enough data. We only have 700 people, right? So dividing them into clusters, into 5 clusters, means that they're like 100, 200 people in each cluster. So it may not actually be enough to train the model over there. And it could be that you see the overfitting is quite high, and so you probably need to look at these factors as well. But again, I could interpret the data in terms of the nonlinear effects. And interestingly, sorry, I'll go here. So the main risk factor is nodes, right? Nodes is number of positive lymph nodes. And then it goes into progesterone and estrogen levels, but nodes are quite important, and so it probably means that there is some switch or qualitative change in survival for nodes below 10 and 4, especially for 4, right? So they separate the population at 4 nodes quite strongly. And by looking at Ensemble 3, kind of the interpretation that I got is that if number of nodes is below 4, then there is a progesterone, which defines the hazard ratio. If nodes more than 4, then another threshold for progesterone defines better the hazard ratio. And there is also, in this particular data, what's interesting, there is non-linearity in the progesterone impact. So the normally the higher, right, the worse it is for a patient. But these results, if you kind of look closer to them, it shows that for a smaller number of nodes, the dependency is reversed. I would probably say that's because we don't have enough data in that cluster, but this particular data has this non-linearity that was caught by the ensemble method number 3. So finally, wrapping up here, this is the final table So here I show discrimination, calibration, stability, linear versus nonlinear separation, interpretation, and number of model parameters, right? So here you can see, so green is good, red is bad. And I guess the most green in terms of discrimination, calibration, and ensemble method number 1. But then it's quite difficult to interpret because what we did is we just trained random forest on top of Cox model. So at the end, it's just survival random forest. So it's still difficult to interpret the results, right? And there's like medium number of parameters, and it did tend to overfit. The next one and the most rounded, I'd say, is probably ensemble method number 3 for the reason of being good here, because this is where we got the most insight into where there's nonlinearity. If we didn't know the data, that's where we would see where it is, right? Because this ensemble method number 3 but identified automatically where the nonlinearity terms were, and was quite good in it. So I think that's the ensemble number 3. And ensemble number 2A was also quite good, and it's quite easy to interpret, but it has more parameters because we basically, for each cluster, we did its own regression, right? Cox regression. So the number of parameters is quite high. So overall, I'd say the best overall is ensemble number 3. Best predictions were, for example, number 1, and I'd say the runner-up is ensemble number 2A. And that was actually quite sad because I really liked ensemble number 2A because that was kind of my idea, which wasn't really presented before, but I have some ideas about how to improve it so that ensemble number 2A would work better. But I should admit that ensemble number 3 was probably the best. So what are the conclusions? Is that classical methods work very well for predominantly linear dependencies, that the combination methods can be very helpful for complex data, that presented ensemble methods can give an insight into nonlinearity, and that's pretty cool because I found it's a little bit like magic that it did find everything that I modeled. That ensemble methods are particularly useful in presence of the cross terms, that we saw the best the most marginal improvement, right, compared to Cox model. And that for smaller samples, for smaller sample sizes, I think that probably should be for ensemble number 3 or just the Cox model, just because you don't split the population too much, right? If you don't have many people to split to start with, so you shouldn't really do that. Further steps are we can further improve nested cross-validation. Also have some ideas about how to, because we saw that the way we build the tree differed the results a lot, and the one method was much better than the other. So I think by writing my own or our own splitting rule targeted for the ensemble method I'm trying to implement could further boost its performance. And I'll try to user-friendly to kind of write the function in user-friendly way. So if you wanted the R code, I could just give it to you and you run it on your data and it'll show you all the results that I presented here in a nice way. Now, finally, thank you very much. I hope I did not lose many of you on slides number 4 or 5. And I particularly thank Daniel and Angus, my 2 supervisors. I thank all of you, the prediction modeling team, those who joined today, the Biomedical Research Center Nucleus, for allowing this presentation to happen. Raquel for hosting or not hosting, but for organizing this talk, and for Alisa because she was the one who inspired the ELSA study, our analysis of ELSA study, and why I started being interested so much in survival model as well. So now, please, any questions?
Okay, thank you, Diana, for this really interesting and precise talk. So are there any questions? You can also put them in the chat if you want. We have got a few minutes time. And I saw that you can also contact Diana. She present your email address if you're interested in more details. Any questions? Are there? Isabel?
Hi, yeah, thanks for a great talk, Diana. That was really interesting. It was so good. I just wanted to ask a little bit more about when you were mentioning the fact that it might have been able to disentangle the age effect, but you didn't allow as many layers to the tree, and like how you decide how many layers to allow or not. Like I didn't, maybe I missed like whether you decide that prior to the analysis or it's part of like the analysis. Yeah. You're muted, I think.
Thank you, Isabel. So it's a very good question. The answer that right now I did it by performance. So I had the nested cross validation, and the depth of the tree between I think 2 and 10 or 2 and 8, yes, was one of the parameters. So it kind of, so the depth was automatically chosen by the best performance, right? But it wasn't chosen by the best interpretation in a way. So
Cool, thank you. Thanks for a great talk.
Okay, that was a good question. Any other questions? There is a question in the, excuse my ignorance, but what computational burden does the ensemble number 3 method entail? In other words, if you were use it on genetic data that comes from ELSA, would that be feasible? So is it computational? Can you do it with 100,000 SNPs data?
Well, I think it's feasible if you you just need to add the regularization term. So basically, I suggest that instead of Cox, you do the Lassa Cox, so such that you can, you can auto select the genetic data that that correlates with the outcome. But the way we did it is we just use single. So we did it. I think the way we did it is probably better in a way that it doesn't underpower the model, because we only use the polygenic risk score. So polygenic risk score is already like a linear combination of all the genetic components, right? But the way we computed it, we didn't just use our data, we used like the consortium data for that, right? Where you found the odds ratio, etc., etc. From there, you just get the single number which represents the total load, genetic load. So instead of using many genetic factors, we just use like a combined measure of all of them. And we were not really bounded by what are the 6,000 people we had. We kind of, in this combined measure, we used the previous results of millions of people, right? From there, we can just send our data and get the polygenic score, like a total load of genetic load. But if you are to use many genetic variants, then I'd suggest it's best to use Cox Lassa for that. So like basically ensemble number 3 should work, but you just need to add regularization to it.
Okay. Any other questions? I think there's one, Daniel. Oh, sorry, you can Zhang?
Thank you. Thank you for a great talk. I think this ensemble method is very interesting, and you used it for a Cox model. Do you think it's generalizable to other classification tasks beyond the Cox model? I think it could be, right? Do you have any ideas, or do you know some existing works on this?
Yes, I actually know quite few. I didn't want to overburden the presentation, but basically I have a few slides. I can send it to you. So it has the links to the other works that inspired me. But basically there are different ways. So for example, you can actually use the whole survival random tree or survival random forest, and just instead of a few clusters, you have like millions of clusters, right? And then you have all of them you use in the next Cox model, but then you use very high regularization term on top. So basically you can make it as funky as you want, but I kind of kept my focus on the interpretability. That's why I specifically limited the number of clusters and specifically limited to Cox regression, because it averages over time as well, because it doesn't has like time dependent variables, etc. It kind of crudely averages the whole thing to linear terms, and then on top you use some clustering. So I kind of wanted to keep it simple, but obviously, yes, you can do different. And also I used survival methods specifically, but some other people, they suggest, for example, you do the first step, you use the survival random forest, right? But then the second step, you do classification. You just cut the time. You say, okay, I just interested in this time. And then you have ones or zeros for event happen or not. And then you just use classificator as the second step. Right, but then you will lose everything which is censored before that time, because you can't use a classification algorithm. But if you're not censored so much by that time, then you're fine.
Thank you so much. Yeah, these are really interesting. Thank you.
Okay, I think that's a last question by Daniel Stamati.
Thank you, Daniel, and thanks very much, Diana, for the interesting talk. Very interesting combination of techniques and with a very clear purpose. I was wondering, just a quick question on a small detail. When you combine the two models, I think in the first ensemble method you called it, so you apply Cox first, and then on top you apply the survival trees, for instance. I was wondering if you use this kind of, you do it in the same fashion like in the stacking, where you use different samples of the data. For instance, on the first sample, you do the Cox, and then on another sample, you train the trees. Or you use the same sample for both.
So here I tried two ways. So one was that, so you do the train and test, and for the train you separate in two things, and then you kind of train on one part, and then you apply survival on the second part, and then you kind of do the opposite for the second part, but then use the whole thing for random forest. But yeah, I mean, you kind of separate the techniques.
The whole training set for the, sorry, go ahead, sorry.
Sorry, so basically, for example, we have a train set, which is 80% of the data. There's 80% you divide into two parts, which is 40 and 40. And then on the first 40, you train your Cox, and then you imply the survival for the second 40, and then you do the opposite for this one. So that you kind of, you used the survival probabilities, like kind of already tested, right, on that 80%. But then I used the whole 80% with this kind of convoluted survival probabilities to go into the random forest. So for random forest, I didn't separate like you did, but I did for survival itself.
Okay, so a little bit like in the stacking.
Yes.
Yeah, this will give the chance to the second model actually not to look into the prediction of the first one, because it will have seen the labels, the outcome. So the second model have the chance actually to do its work, really do a real prediction. Yeah. Okay, so it's a bit like in stacking, I understand. Okay, thank you. Very interesting talk. Thank you.
Thank you. Yes.
Okay, great. Thanks a lot again, Diana. Are there the last question besides the name of the cat?
Hi, just the last comment, Diane and Daniel. Thank you so much for such an amazing presentation. I couldn't get my eyes off the screen, and the slides are absolutely amazing. So I was wondering, Diane, if there's any chance you might be able to share your slides with us, just for future references and just to draw inspiration from your approach to the data analysis.
Yeah, definitely. So I can upload it. I need to probably just delete everything that I didn't present, and then I can
Well, don't do anything, just send it as is. And
links and references as well. So yes.
That'll be fantastic. And I think your cat has done an amazing job really to keep us our attention going, really. It was adorable.
Thank you. The cat's name is Latte, like coffee. So.
Good name.
Okay, so the recording will be on the BRC prediction modeling page, and we can then also upload the PowerPoint presentation and some references. So that's not a problem. Okay, then thanks a lot again, Diane.